11.4 is called the comparison tests. We're going to learn two new tests here, and they're a little bit different than the tests that we've seen before. So the tests that we've learned, we're going to recap them here as we look at this intro example. But for us, we've learned the geometric series test, we've learned the divergence test, we've learned the telescoping series test, and in 11.3 we learned the integral test and the p-series test. So we're going to start off this example by going through each of these and seeing that none of them will work, but one of the tests is actually going to be like, oh, if that one thing wasn't happening, then we could use this test. So the comparison tests are when one of the tests that we know already is not applicable as the series stands, but with a small adjustment, we could get it to work. And maybe you even can see what that will be, but let's just go through them one at a time. So I'm going to start, hey, could we apply the geometric series test to this series? Well, no, geometric series is a r to the n. That's nothing like what I see there, so definitely not going to work. Could we use the divergence test? Well, let's think. We don't know. But if we take the limit of our nth term and we do not get 0, then we know it diverges. Boom, done. But here, if I take the limit of my nth term, I get 1 over infinity. That will go to 0, and so I don't have an answer for the divergence test. It's inconclusive, you might say. All right, how about the telescoping series? Nope. Telescoping series, oftentimes you use partial fractions at the beginning, and yeah, we're not going to factor that or use partial fractions on this one, not the telescoping series. How about an integral test? And you're like, well, maybe, right? I mean, I don't know. If we were to use an integral test, kind of the key when just thinking about that, sorry, this is pretty tiny on my paper. Obviously, there's the three conditions on f of x, 1 over x to the fourth plus 3. But just think to yourself, in your head, could you take that antiderivative, right? Imagine, like, could you take an antiderivative of your nth term? And okay, so I just noted, maybe we could, but again, I think that would need like maybe a partial fractions, or I'm not exactly sure what. There might be an antiderivative out there somewhere, but if there is, that's hard. So if it's immediately obvious that you could take an antiderivative, maybe it needs a u sub or by parts. It doesn't mean it's an easy one. But if it's possible, then it's very likely you could use integral test. Here, though, yeah, I don't know what we would do. I'm just going to say that's hard. I don't know. How about p-series? This is the last one, the last test we know, right? P-series applies to 1 over n to the p, right? One over n to the p. If I know what p is, I can tell right away. Well, no, this is not a p-series, but it's so close. If that plus 3 was not part of this, I would know it's a p-series and I'd have the answer right away. That plus 3 just throws it off a little bit. So I cannot apply p-series as it is. But because it's close, I'm going to do a comparison. Okay, so this is what I've got on the other side. I'm going to compare my original series with what it would be if I removed that one stubborn part. So if I get rid of the plus 3, well, of course, I would have 1 over n to the fourth. And then I'm going to put an inequality between them. And that's how I'm comparing. Well, would it be a less than or a greater than between these? Is this one bigger or is this one bigger? Here's how I think of it. And that's a little bit off the screen. So, okay. Look at what happened, right? So if I get rid of this 3, then my new denominator is smaller than the original. My new denominator is smaller. Well, if the denominator is smaller, then didn't the entire thing actually get bigger? So for each value of n, right, n equals 1 would be 1 over 1/4, or 1 over 4, 1/4. Here n equals 1 would be 1 over 1, 1. Well, 1/4 and 1, this one is the bigger one. My new denominator got smaller, so the whole thing got bigger. I'm going to play it really safe and throw an or equal in there. And I don't think you really need that here, but there might be series where sometimes it gets bigger, sometimes it's actually equal. It's kind of that monotonically bigger sort of thinking. It's never getting smaller, right? It's at least equal, if not bigger. Okay, so that's key. Now I can answer about this new series. My new series converges by the p-series test, right? P equals 4. P equals 4, which is greater than 1. So it converges by the p-series test. Well, hey, here's the logic. If this one converges and it's always bigger than this one, every individual term is bigger or equal, and it converges, then certainly if I make the term smaller, it's still going to converge. And that's true. So I can say the series that I'm questioning, 1 over n to the 4th plus 3, converges. And here we like an abbreviation. We're going to call it DCT. It stands for Direct Comparison Test. All right, that's a great, simple introductory example. Now let me show you the test officially. There will be another comparison test as well a little bit later. Here's the simpler of the two, the direct comparison test, otherwise known as DCT. So take a moment, copy that over. So it begins by saying, let 0 be less than or equal to a n less than or equal to b n for all n. We're saying that, right, a n is caught between 0 and b n. They're always positive values, and b n is always at least as big as a n, usually bigger, I think we might say. So there's two different ways of looking at this. If your series for bn converges, right, bn is the bigger one. If the bigger one converges, then the smaller one must also converge. That's exactly what we saw in that last example. We created a new series that we knew was always bigger or equal to. We showed that that converges, so the series with terms smaller must converge as well. But you could think of it from the other perspective. What if the smaller one diverges? Well, then the bigger one has to diverge as well. If each term gets larger or equal to, more importantly, it at least is equal, if not bigger, when you make the bigger. And this diverges, the smaller. All right, okay. I think I'm saying too much. If the smaller one diverges, the bigger one diverges. Very nice. We've got a couple of examples. Two. We could probably say we've already done one. So let's dive into this. The question, of course, is simply, does the series converge or diverge? And we just have to know what test to apply, and there's some guess and check there, right? Obviously here we're going to use direct comparison test, right? That's no surprise. From 1 to infinity, 1 over 2 square root n minus 1. Okay. So what about this, and there might be multiple things, what about this is like getting in our way from almost immediately answering? And kind of like in the last one, it has a similar feel, right? I think this minus 1 If that wasn't there, we could do something. You might say the 2 as well, but it turns out the 2 multiplying really isn't a big deal at all. It's that minus 1. So here's what I'm going to do. Often you'll see when people are kind of brainstorming this to the side, this is like work on the side, if you will. They don't write all the details on the sigma. They just write the sigma and then the thing and then the sigma and then the new one that they want to compare it with, and leave that spot in the middle blank, and then carefully figure out, is it a greater than or equal to, or is it a less than or equal to? And be careful with that, because if you get it backwards, then that could be really bad logically. Or you might not think you have an answer and you do, that sort of thing. Or the other way, you might think you have an answer but really you don't. Let's see, is this new one, did it get bigger or did it get smaller? This time our denominator actually got bigger, right? We added 1. So if our denominator got bigger, then the whole thing actually got smaller. And you could even try out a value, maybe like 1, right? So at 1, I've got 2 minus 1 is 1, 1 over 1. At n equals 1, this whole thing is 1. Here at n equals 1, I get a half. Well, 1 is bigger than a half, right? Okay. All right. So I can tell I made it smaller by getting rid of the minus 1. Now, for those of you who are thinking, oh, what about the 2? Could I get rid of the 2? Well, sometimes you do this more than once, and you can create another one and just keep the chain going. So what if we got rid of the 2? And now we really like that, right? Into the 1/2, we can use a p-series. Pretty common with comparison tests, actually, to go with p-series. What happened this time compared to the last phase? From here to here. If I get rid of the 2, then the denominator got smaller, which means the whole thing got bigger. And this is not good. So I made it smaller, but then I made it bigger. I have no idea how this compares to the original. If it kept getting smaller each time, then I would know the new one is smaller. But because it went from smaller to bigger, I want to get rid of this. I just want to ignore this. That was some brainstorming. I was hoping maybe I get rid of the 2 as well. Turns out I have to be consistent, right? I always have to go the same direction. So I have no idea how this compares to the original. But I do this one. Okay. So here's what we're going to do. We're going to look at our series here, and we'll fill it in now. N equals 1 to infinity. Hey, why is that 2 actually not an issue at all? Because I can just bring it out, right? 1/2. Just like an integral or a derivative. No problem. And I'll think of it as 1 over n to the 1/2. Well, as we mentioned a moment ago, that's a p-series where p equals 1/2. And if you look back at p-series, it'd be nice if we were in class and be like, hey, if p equals 1/2, what does that mean? Does it converge or diverge? Well, if p equals 1/2, that's less than 1, so it diverges. That series right there diverges. Obviously, if it diverges and you multiply by 1/2, that's going to diverge. Okay, so if this diverges, if that diverges, can we conclude something about this one? Well, if the smaller one diverges, then the bigger one has to diverge as well. That's the second part of the DCT. We know the original series 1 over 2 square root n minus 1 diverges by DCT. And now this is big, and now you really see why stating the series, the test is important. And here I even went and rewrote the series, so there was no question about it. Everybody knew which series I was talking about when I made this final statement. I would definitely not want to conclude with this line. Hey, this diverges. Okay, done. No way. I need to say it diverges. I need to say it's by the p-series test. But then I have to make the logical connection here and say because this diverges by p-series test, then I know the original series diverges by the direct comparison test. So there's always two tests working in a comparison test. There's your, in this case, your direct comparison test, and then like part of that is the p-series test. So we use the p-series as leverage to make the comparison, and now we can say this. And I have to write that as my final statement. Okay, you guys get it. We're at about 16 minutes, so I'm going to stop here. Another example and the second comparison test in the next video.